the nature of distributions is such that whenever we talk about distributions, it will be a population. All right, so when you say I'm using normal distribution to describe the heights of all students in my university, that means you are asserting. Assert means state without proof. Yeah. So you are saying that I know all the heights of students in the university. Now, most likely that is not true, right? But this is often acceptable because when we say the heights of students in my university follow normal distribution with a mean of 1.6 and a standard deviation of 10 cm. So that is acceptable, even though no everyone knows, you probably haven't measured every single student's height, but it is an acceptable model because it is the properties match. You're applying normal distributions pretty appropriately, as we'll see later on when and where we can apply normal distributions. And you are making a model. You are asserting without proof that this normal distribution describes the entire population of heights of the students in your university accurately. Right? So we accept this model because the properties match, and then from there on, we derive understanding from normal distribution and say, okay, based on normal distribution, I think 5% of people will be from 1.8 meters to and above. Yeah, so you can make claims like that just based on this assumption. So every time we say it follows certain distribution, even if it is not one of the standard distributions, but it is an arbitrarily created distribution, whenever we use the word distribution, the author, the one who says it, means population. And the one who reads it must interpret it as population of measurements. It will never be representing a sample. Yeah, okay. Next, when we talk about distributions, there'll be x and y axis, because that's what is in my mind. Each outcome, meaning each value, and each value on the x-axis has to be unique. Yeah, each value on the x-axis will be independently occurring. So in other words, if an event occurs with a measurement value, let's just put everything into a number of 3, then the appearance of 3 neither makes 4, 5, 6 more likely or less likely. Yeah, okay. Now, if you have a bag of cards, let's say just 10 cards, yeah, and for simplicity, let's just say 5 cards are 3, and then 3 cards 4, and then 2 cards 5. Yeah, so 3, 4, 5, just 3 numbers, and then quantities 5, 3, 2, so that there are 10 cards. Now, if I give you one card called 3, you're going to say, well, it is going to reduce the probability of 3 occurring in future, isn't it? Because you know that there are 5 cards. If I give you one card, you know that I'm limited to 4, right? So I cannot be continuously giving you 3. It will never happen because you know there are a limited number of 3 cards in the cards with number 3 in my bag. So in that case, then it is no longer independent. The occurrence of a card number 3, or 4 or 5 for that matter, will affect future occurrence of 3 itself, or for that matter, maybe other cards. But in this example, if I give you a card number that's 3, you know for sure that in future, the probability of 3 occurring will be less. Yeah? So that is how it may not become independent. So for a distribution to be sort of standardized, and then for it to be called distribution, the outcomes shouldn't affect each other. Okay, so this is often taken for granted, but I just want to make sure this is built in because we talked about this notion earlier on. The other 2 properties, we have learned them earlier on, and we want to sort of revisit them in association with this new topic called distributions. And that is that all the outcomes, remember all the outcomes, they all fall on x-axis, because when they occur again and again, then they start stacking up on the y-axis as relative frequencies. So all the outcomes do not overlap. That is kind of, again, taken for granted. If a number is 3, that is 3, right? It will not overlap 4. Yeah, but we may have x-axis that are qualitative labels. Qualitative labels. So if they are qualitative labels, they should be labeled in a way that is mutually exclusive and at the same time exhaustive. So let's talk about mutual exclusivity. If we have a dice that don't have numbers but just colors, red, orange, green, blue, yeah. So if you throw and we just look at the top side of the dice, then each color is mutually exclusive with other colors, right? Because if it's red, it cannot be yellow, it cannot be green, so that's quite clear. So then you wonder, how can it not be mutually exclusive? Well, we can take a dice, the usual 1, 2, 3, 4, 5, 6 dice, and say start labeling the attributes small numbers, medium numbers, large numbers. So instead of labeling 1 to 6, we say small, medium, large numbers. And we say small is 1 to 3. 1, 2, and 3 inclusive. Medium is 2 to 5. Large is 4, 5, 6. Aha, now you start to see that that is a poor definition, right? That is overlapping. Like it's like 3 is both small and medium. So it's ill-defined. It's not properly defined in such a way that the outcome, for example, 3, is mutually exclusive. Because now if I see a number 3 being shown on the dice, should I say it is small number? Wait, it is also a medium number, right? Because it's 2 to 5. So we have a problem there. It's not mutually exclusive. Then you cannot call this a distribution. Now, finally, we must have the exhaustive listing of all possible outcomes on the x-axis. So if you throw a dice, can you write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Answer is yes. You have overwritten. Have you observed mutual exclusivity? Yes. 1, 2, 1 and 2, 2 cannot be 1, 1 cannot be 2. Is it exhaustive? Yes, because the dice can produce 1 to 6. You have written all of them and more, 7, 8, 9, 10. So the frequency of occurrences and hence the probabilities will always be 0. And that's okay. It's not undefined. It's not problematic. Yeah. So 1 or even 0 to 10, that's okay. But we'll see frequencies. We'll see the y-axis rising above 0 only for the values 1, 2, 3 to 6. Yeah. So we did exhibit this exhaustive property of the distribution. So that's fine as a distribution. How about a distribution of the dice where we write 1 to 3, 1, 2, and 3 without listing 4, 5, and 6? What happens when you throw a dice and the face shows 4? And then we are in trouble, right? So that cannot be done, and that's inappropriate. So we have a mismatch between reality and your proposed distribution to describe this reality. So not okay to apply your distribution when the x-axis is just 1, 2, and 3. Yeah. So we wrap up this intro of distributions by talking about the discrete and continuous nature of distributions. So distributions, right? There are always populations, and there are two classes of it. One is called discrete, one is called continuous. Easiest way to think about it is that when you draw a diagram, a histogram, discrete distributions or continuous distributions, they are talking about the discreteness, the one piece by one piece nature on the x-axis only. Yeah. So this is discrete with only 6 points. This is discrete with all the integers, maybe up to 50. This, however, is continuous. So all numbers between A to B are possible. If A is 1, B is 6, then 3.145 is entirely possible. 3.14159265335 is still possible, right? So any number of decimal places that you append onto it is possible, so long as the magnitude doesn't go below 1 and go beyond 6. So that's the nature of continuity. So discrete or continuous case, they only describe the nature on the x-axis. Is it dotty, dot by dot, point by point occurrences, or is it one whole continuous range, right? I mean, what textbooks like to use this example and say, if you can use a pencil, and continuously complete the x-axis values from start to finish in a without lifting up your pen, right? Then that is continuous distribution, and otherwise it is a discrete distribution. So you have to often lift up your pen, put down again on 2, lift up your pen, put down again on 3. So that's the nature of discreteness and continuity. Now, what about the y-axis? Y-axis is always continuous, right? We never we never worry or bother about the y-axis being discrete because most values will be below 1 anyway. So it has to be continuous. So y values, it's a probability density basically, or probability density. So it will be a value below 1, and it doesn't matter even if it goes beyond 1, above 1. So it's continuous in nature. Any value, any number of decimal places can occur. Okay, so the discrete or continuity of it, nature of it, is only about the x-axis. Number 2, x taking up point value. So 1, 2, and 3, right? So let's look at the first graph, 1 to 6. This is number 1, discrete, and it is finite because it stops at 6. So basically the probability occurring for 7, 8, 9, 10, and so on until infinity, it's really 0. So in some sense, we'll just say that x goes from 1 to 6 inclusive. And because 6 is finite, it's below infinity, we'll say it's a finite discrete distribution. Finite is just that, it's limited in the maximum value. And in this case, suppose the indication, the arrow, is just to show, well, it can actually go to infinity with a tiny little probability on the y-axis, right? So 1 times 10 to the power minus 16 and so on. So it can go to a very low height, but it's never quite 0 until it reaches infinity. Then the range of x will actually extend to infinity, and in that case, we will call that a discrete distribution with infinite x values.